Yeah. So very good afternoon to all the participants. We are back again with the fifth session in our international webinar series. So I hope all participants are enjoying the lectures, and yeah, it appears from the participation, the interactive session as well. So we expect similar interaction in this session as well. So for this session, we have Dr. Biswajit Dev from Sikkim Manipal Institute of Technology, Sikkim, and he will be talking on graph theory, a theory of modeling in for social and scientific problems. So Vishwajit sir, you are on screen now. Welcome to our international webinar session. It's very nice to have you with us.
Thank you.
Uh, yeah, can you hear me?
Yes, I can hear you.
Yeah. Okay. Okay, so we have also have our student Rahul Pal with us. Rahul, please unmute yourself. Yeah. Okay. So Rahul Pal will read out the biodata of our speaker. Rahul, you can start.
Good afternoon, everyone. I am Rahul Pal, a fourth semester BSc Mathematics honors student from Gurucharan College, Silchar. First, I would like to thank to our sir, Dr. Debashish Sharma, for giving me such an opportunity to introduce our invited speaker, Dr. Biswajit Dev. Dr. Biswajit Dev is currently working as an associate professor in the Department of Mathematics, Sikkim Manipal Institute of Technology, SMU, Sikkim. He completed his MSc degree in mathematics from Guwahati University in the year 2000-2001 and was awarded the Doctor of Philosophy Award from IIT Guwahati in the year 2013. He has more than 18 years of experience in teaching undergraduate and graduate students. Apart from teaching, he is also active in research and presently 3 scholars are pursuing under his guidance. His primary research area is graph theory. Presently, he is working on sign graphs, topological indices of graphs, and motion planning problems in graphs. Now we are looking forward to an interesting lecture from our invited speaker, Dr. Biswajit Dev. Forward to Dr. Debashish Sharma sir for continuation.
Thank you, Rahul. I am putting you backstage now. No, sorry. Okay, so without further delay, I would like to request Dr. Biswajit Dev to begin his talk. So you can share your screen.
Okay. Thank you, Rahul, for the nice introduction. It was indeed a pleasure for me to be a part of this international webinar organized by Devashish, who took lots of pain to organize this during this pandemic period. And in fact, he himself actually was in hospital for quite a few days, just 15 days back. So after that also, he did not give up. He continued his
recovery from coronavirus.
and somehow we are here. And I'm really privileged to be associated with Gurucharan College because I never visited Silchar. In fact, I was supposed to visit this May for some official purpose, but I could not visit. But my best wishes is there to the college and to the department as well. And I hope that they will continue organizing this kind of interactions. Today, without delay, let's go to the topic. I'm going to discuss very important branch of mathematics from application point of view, that is graph theory. And my objective is to give some to the graduate and undergraduate students some exposure to the graph theory without going into the details of the graph theory, where and what kind of works is going on, and how important it is from application point of view, the subject. So we will be discussing two problems, two application area first, and then we will discuss some research problem as well. If somebody interested, I will discuss some open problems as well, a broad area of an open problem. If somebody interested, they can later associate it, can associate it with me also to work further. So without delay, let's go to the uh, presentation.
Yeah, you can share
I'm
your
sharing
screen.
my screen. Is my
Yeah,
screen shared?
yeah, it's shared. It's visible. You can open the presentation. Yeah, it's. Oh, is it in?
Is it visible?
Yeah, it's visible, but it's not full screen. I think you can make it full screen. It has opened in journal, I
Just a
think.
moment.
Yeah.
Yes, because I wanted to see some of
Oh,
draw something
oh,
during interaction, so that's why.
oh, okay, okay.
Is it
Okay, I
okay?
think.
Let me see the view. Okay, I will take 2 minutes to
Yeah,
set up the things. Just a
yeah.
moment.
Okay. Meanwhile, for the participants, just like the other sessions, the feedback link will be provided at the end of the session. And for the earlier lecture, also feedback was provided, and the feedback is also available in the comment of the YouTube video. You can have a look at the YouTube video if you have not got during the live session. Yeah. So, okay. Sir, shall I add the screen now?
Just a moment.
Yeah.
1 minute. Yeah, you can add now.
Okay. Yeah, it's there.
It's looking small, right?
Mm, yeah. Can you please change? Means one slide. Next, if you please go to the next slide. Yeah, yeah. I think it's yeah, it's visible, but
Now is it okay?
when you change the slides, it's not changing. Means it's not in full screen. I think means it's not in slideshow format.
Is it okay now?
Yeah,
It's
this is
changing now.
visible. Yeah, yeah, yeah. It's changing slide wise. Yeah. Okay, okay. Yeah, it's okay now. Yeah, it's visible. The font is quite large. It's visible. Okay. Okay, you can start, sir. Yeah, this is okay.
So let's
So I'm going
begin
backstage.
this talk. Uh, I'm in backstage, or you can put me in like.
You are in front stage. I am in backstage. So participants can see the
Okay.
slides also. They can see you also. If means sometimes I will enlarge the slides. If the font is small, okay, I'll do that
Okay.
accordingly.
Okay. So can I start?
Yes, sir. You can start.
Okay. So let's. I'm not going to the details of the graph theory at the beginning. So I'll be discussing the definition, and then whatever new concept we will be required during the discussion of the problem, we will discuss it at that point of time. Even if somebody is not means exposed to graph theory, they will be able to understand with little bit of hardship. Okay. Let's what we are I'm going to discuss is that what is graph, then and one area of application, that is using coloring of a graph. Uh, then minimizing a switching function, which is an application in digital circuit network. Then some open problem in the field of emerging reachability in graphs. And then one another type of graphs we are going to introduce, although I'm not going to introduce weighted graphs, but is a special kind of weighted graph that we are going to introduce to discuss one social problem of healthy relationship between a group of people. Now, first of all, what is graph? So to begin with, let us take two sets. Okay, so we start with two sets. One set is V, having some numbers arbitrarily chosen, and then another set EV, where we are collecting pairs I comma j, where we are collecting pairs I comma j, such that GCD of I comma j equal to 1 and I comma j is a member of V. So I'm taking two members from V, and the corresponding two-member set is a part of E if their GCD is 1. So we have this setup. Can we represent this using a diagram? That is what we want to know. Okay, and the answer is yes. Let us try to do this. So what we can do here, for each of the members in the set V, we put some dots and represent the members of V by writing the corresponding numbers in front of the dots. Now, what is the collection in the set E? It's a pair of objects from the set V, such that the GCD of the pairs is equal to 1. Now, if I look into this, GCD of 15 and 19, what is GCD of 15 and 19? It is 1. So just to represent that the GCD is 1, it is satisfying the requirement. So we can put one age, just join them. So just representing that these two are related by the relation that we have described in E, that kind of thing. Okay. So similarly, 3 and 14 have GCD 1, so that can also be represented by this. Then 3 and 49 GCD 1, and so on. Okay, so this diagram actually keeping the information of those two sets, but at the same time we must have an information what this dots represent, what this ages represents here, what this line represents here. Okay, what this line represents here. So this line, as you know, this line this lines actually represents that GCD of the two numbers by the end represented by their end is 1. So that is what you have to remember to this. So this kind of structures are known as graphs. So we have now, let us go back to the reverse process. Now we have a structure. Now can we represent it by using sets? Okay, so if it is possible, then this representation is fruitful, because we will be able to go from the set theoretic representation to the graph theoretic diagrammatic representation, and then diagrammatic to graph theoretic representation. Okay, so let us see the formal definition of graph first. What is a graph? A graph consists of two sets. Okay, so one set is a non-empty set V. Okay, and the other set is a set E of subsets of V of size 2. So we are collecting in the set E subsets of V of size 2. Remember here, when I say subsets, it has meaning. So the members of E are nothing but sets, and we know what are the properties of a set. Okay. Now, under this setup, if I write down the set theoretic representation of this picture, so my vertex set V will be my vertex set. So it will contain the label of the vertices. Okay, 1, 2, 3, 4, 5, 6, and E will contain the pairs. Okay, say 1 and 6 is adjacent, so we have 1 and 6 in the collection. 1 and 2 is adjacent, so we have 1 and 2 in the collection. So and so on. Say 1 and 4 is not adjacent, so we don't have the pair 1 and 4 in this collection. So that is how we represent a graph. Okay. So we can represent a graph by a diagram, as well as we can represent a graph using sets as well. Okay. So let's, without delay, let's move to application area of graphs. So that is coloring of graphs. So before we move to application, so let us understand what we mean by coloring of graphs. Okay. Coloring of graphs means assigning color to the vertices in such a way that two vertices that are adjacent, they do not receive the same color. Okay. Adjacent vertices, they receive the same. Adjacent vertices receive different color. Okay. Now, uh, parallel to coloring, there is another word used for used by the graph theorist, and that is known as leveling of a graph. So instead of assigning colors, you can also assign levels to the vertices. Okay. So leveling of graphs is nothing but assigning integer level to the vertices in such a way that the difference between the levels of the adjacent vertices is at least 1. So it means if the difference is at least 1, definitely the levels of the adjacent vertices are going to be different. Okay. So it is not actually satisfying the requirement of the coloring as well. Okay. Coloring as well. But leveling has more generalized setup. So in fact, there are different kinds of leveling has been discussed recently, depending upon the application in different areas. So I will give 2-3 application areas of leveling as well later, without going into detail. Now, let us try to understand what we mean by coloring. So let us take this graph. So when I say that coloring is nothing but assigning colors to the vertices in such a way that no two adjacent vertices receive the same color. So what we can do to color this the vertices of the graph? So we can assign color red to 2 and then red to 5 as well, because 2 and 5, they are not adjacent to each other. Now, apart from that, can I apply any color to the vertices to any of the graph? The answer is no, because 1 and 4 is adjacent to 2, which is already red, and 3 is adjacent to 5, which is already red. So red color cannot be allotted to any of the vertices. So next, we take another color and assign it to 3 and 1. Okay, and now we have 4 left, so we assign another color, green. Now the question is, in this graph, can we color the vertices in this graph with 2 colors? Because we are always greedy. Okay? That is the main issue in coloring. Coloring the vertices of a graph with as many colors as you want is not you would like to have. What will be your intention is that you would like to color the vertices of the graph in such a way that you utilize minimum colors. We always have a habit of using minimum resources. So we would not like to have as many colors, say, because 5 colors if I use, definitely no adjacent vertices are going to receive the same color in this graph. But we have used here 3 colors. Okay. But the next question is, can we use less than 3 colors? The answer is no here. Very easy to understand this concept. If you look into this 3 vertices here, so they are forming a triangle. They are adjacent to each other. Now, if you look into this 3 vertices, you need at least 3 colors to color this 3 vertices. So that's why in the whole graph, you need at least 3 colors. So with 2 colors, it is not possible. Okay. But remember, when we do coloring, we always try to color the vertices with minimum number of colors. That is the main problem here, and this is very challenging problem. It's not that easy problem. Now, how many colors do we need to color the vertices of a graph properly? So So there are some quick bounds you can see is that if you have a maximum degree in the graph delta G, then you need at least you can do the proper coloring using delta G plus 1. Okay, you can properly color the vertices using delta G plus 1. Okay, so let's try to understand this through this graph. So what we have here is this vertex has degree 4, and this result says that 4 plus 1 colors is sufficient to color the vertices of the graph. But in this graph we have used only 2 colors. So it means that this delta G plus 1 is not a good bound for the coloring. Okay, it's not a good bound for the coloring. Suppose we have a 1000 vertex graph similar to this. Okay, so we have one central vertex and all the remaining vertices are adjacent to that central vertex. So this bounds that we need 1000 colors to color the vertices of the graph, whereas 2 colors are sufficient. Where is 1000, and what is instead of that 2 colors are sufficient. So that's why this bound is not that sharp. Okay, that's sharp. So clearly delta G plus 1 is not a good bound. In fact, the main issue in coloring is coloring with minimum number of colors, and there is a famous theorem which took almost 100 years to solve, is the 4-color theorem. Okay, any planar graph can be colored using 4 colors. So what is planar graph? So that is again another area of graph theory. So I'm not going to discuss that, but remember, any planar graph can be colored using 4 colors, irrespective of the number of vertices it has. So for example, this graph, if I take this graph, this is an example of a planar graph. This is an example of a planar graph. So planar graph is a graph in which no 2 edges actually cross each other. But the moment I increase the number of vertices here by 1 and keep on adding edges, I will see that there will be one situation when I won't be able to draw any more edges. So for example, this is the situation. So I have one option to draw one edge, but I'm unable to do that. Okay, I'm unable to do that. I have an option to draw this edge, but I'm unable to do that. Okay, so that if I draw it, it is not planar because this crossing is taking place. Okay, so that is what we mean by planar graph. If you can draw the graph in such a way that no 2 edges intersect or cross each other, we will call that graph is planar. So planar graphs are 4 colorable. You can even if you have millions of vertices in a planar graph, you can always color the vertices using only 4 color. So now we have understood the problem of coloring. Now let's move to a simple problem that we can use where you can use coloring to solve the problem. Okay. So for teachers, this is an issue always. Okay, so let's try to understand the problem first. So SME offers 6 papers. The paper codes are given here for 3rd semester MSc students, of which 4 need to be opted by each student. So lots of flexibility. Okay, not 6 actually. We are taking here 7, 8. The students' size is 1000. 1000 students are choosing, so they can choose any of these 4 subjects. But at the end of the semester, we need to conduct the exam. Okay, so we need to conduct the exam. So, but there is no restriction about the combination of the papers. So any student can choose any of these 4 subjects out of these 8 subjects. Okay. the problem is to schedule. What is the problem here? The problem is to schedule the semester examination with minimum number of slots. Okay, see, we have 8 subjects. If we schedule those 8 subjects in 8 different slots, it is going to be time consuming, because 8 different slots need to be used, or 8 different days, or say one day 2 papers, then 4 different days need to be used to conduct the examination. Now the problem is we have to conduct the examination in minimum number of slots. Definitely the number of slots cannot be less than 4, because 4 different subjects one student going to take, and he need to appear in 4 different slots, 4 subjects. Now the question is how many slots we need to conduct the exam for this 8 different subjects. Suppose we have an extra information about this students, that who are the students opting for which subject. That information we have, and we represent it by a graph like this. So what we mean by this graph is that there is a student who took who selected this MA 2308 and as well as MA 2303 as well. Okay, so because we have an age here, so what does age represents? I have a common student who have selected these 2 subjects. Okay, now we do not have adjacency between these 2 vertices. You see, MA 2302 and MA 2306. What does it mean? What does it mean here? MA 2302 and MA 2306, they are not adjacent, or no age between them. So it means no students have selected both these papers. So there may be some students who selected 2302, some student 2306, where there is no common student selecting both these 2 papers. So this is what this graph represents. Now we want to solve this problem of assignment or scheduling the exam. Okay, scheduling the exam. So the suppose we are given 3 different days to conduct the exam, with each day having 2 slots. Now is this enough? Means in 6 days can we conduct the exam, or we will be required more than 6 slots? Sorry, 3 days, 6 slots. So we will be required more than 6 slots. So let us try to see it from coloring point of view. So find a coloring for this graph. I'm not finding the minimum coloring or any process I'm using to get the minimum coloring. I'm arbitrarily putting colors. Okay, so first I assign colors to 01 and 07, because these 2 vertices are not adjacent. So it means their exam can be scheduled on the same day. That is what we are getting information from here. Okay, they can be scheduled in the same day. So next, assign colors to the next 3 vertices. So is 08, 02 and 05. Remember, none of this no pair of these 3 vertices are adjacent, so they can be assigned same color. Okay, so it means that these 3 subjects can also be scheduled at the same time. Okay, now these 2 are not adjacent, they can also be scheduled at the same time. And finally we have MA 2306. Okay, that is left. So it means we can solve this problem even in 4 slots. Okay, even in 4 slots. Okay, but remember, if the number of students goes up and the connection between the vertices in this graph increases, so then it may not be able, we may not be able to solve this problem or schedule the exam in 4 slots. So it definitely depend how the students are choosing the subjects. Okay, how the students is choosing the subjects. Okay, but in a college or in university, it is not scheduling the exam for 1 subject or 1 semester. Remember, it is a problem of scheduling the exam for different subjects, for different courses. process during that 15 days or 1 week time of conducting the semester examination. So the problem is much critical. I have tried to demonstrate the problem through a small example. Okay. You can think of a even bigger problem here. Suppose we want to deploy some new software in the server, in each server of Google. Okay, so remember, to deploy any new software, what we have to do is we have to take the server down. Down means it will not be live during the upgradation. Okay, so the means streaming may get delayed or may get disrupted. Okay, now another side of this is that we need to update all the servers, and if you search in Google, there are around 9 lakh servers, active servers working for Google, and you have to update that, means install that software in each of these servers. Now, can Google afford to take all the servers down and update them together? Not possible. Can they do it one by one? That is also not possible. Doing it one by one for 9 lakh servers for say one updation may take 1 hour. So how many days it will take? So you can think of the problem, quantum of the time, quantum means the gravity of the problem. Okay, here. So what can they do? In this type of situation, coloring may come into role. Recently, in one of the major technical support provider for internet have updated 75,000 servers using only 8 slots. Remember, using only 8 slots, 75,000 servers. Okay, so if you use coloring properly, it can, and in fact they have used coloring only to schedule the updation. Okay, updation process, 75,000 servers in 8 schedules. Okay, so see, a small beginning of coloring can be used such big problems. I'm not going to go into details of these problems, but there are other areas where this coloring can be used, assigning frequencies to radio stations. Okay, here more advanced kind of complicated leveling has been introduced. One of them is known as L2-1 leveling. Then allocating register for program variables. So when you run programs, computer programs, every variable need to be computed. Then this variable need to be assigned some register, and every computer has limited number of registers. Even in 64 bits machine, you have only 32 registers, and your program may involve thousands of variables. So how you assign the register during the computation process? That is an issue is handled by this coloring problem. And remember this, here the concept of dynamic graph also comes, because every time you are in a new loop, your active variable changes, so your graph structure also changing. So accordingly you have to plan your allocation of register to the program variables. So then the famous map coloring problem, many of you have come across of this. Okay, so now let's move to another problem where we can apply a small idea of graph theory to solve a problem. So logical circuits. So logical circuits are important in every electronic devices. Okay, so you will find a logical circuit in every electronic devices. So what is a logical circuit? Let's try to understand first. Okay, but the logical circuit actually involves a function. So the equivalent term of this function is also known as, means in mathematical term, it is Boolean function. So what is Boolean function? It is defined, it's a function defined over a Boolean algebra. Now, what is Boolean algebra? It is the algebra over two element set, say 0, 1. Okay, so this is for digital world, this notation, but mathematician can also understand it using true, false. Okay, true, false. 1 stands for true and f stands for 0 stands for false. So Boolean algebra over this. So two operation, over this true false is join operation and meet operation, and the another one is operation that not binary, unary operation, that is negation. Okay, these three operations are very popular. Other than that also we have many other operations, but these three are enough to understand this Boolean algebra. Okay. So Boolean algebra was introduced by George Boole in 1847, and it was first used by Claude Shannon in Bell Labs in 1938. So most of the times students ask, sir, we are doing some mathematics, where we can use it? Okay, and another thing, this is the question of undergraduate students, but even in research, people doing research in mathematics have been are asked by the users that whatever new results you are getting in your field, where we can use it. Remember, mathematician can give you some understanding about the concept, but it's not duty of the mathematician always to give a field of application. So application people will find it whether it is usable or not. Think into this. In 1847, this concept of Boolean algebra came into existence, and after almost 90 years, after 90 years, its application came in terms of digital circuit. So that's what means. If you are doing something in maths, you are getting some information, so it's worth to note and let others know. So some of the Boolean function we use are popularly known as AND, OR, NOT, and other than that NAND, NOR, XOR. So we don't need these things. So I'll be concentrating on only three parts, because any logical circuit we can draw using these three only. Any whatever complicated it is, but the size of the circuit may increase. But here, what we are going to address is that how we can reduce the size of the circuit. That is what our intention. So here, this is representing, this symbol is representing AND operation, this is representing OR operation, and this is representing the negation operation, unary negation operation. Okay, and how this truth table are constructed, I hope you know. Even if you don't know, it doesn't matter, it's going to be yeah. Now suppose I want to have a structure like this. What it represents here? So when I'm giving input to W, X, Y, Z, W is taken as it is, but X is taken negation of X, and then W and X are joined by the AND operator. So it is WX here, and then Y is negated here, and then again WX and Y is joined by AND operator. So it is WXY. And finally, Z, negation of Z is coming. So from here, and then again WX bar, Y bar, and then Z bar is joined, and to give you the output like WX bar, Y bar, Z bar. So for this information, so if you give any input to this, say for example 1, 1, 1, 1, 1. So what will be the output you can calculate here using that table, previous table. Okay. So that is how the digital circuit are constructed. But this is a small circuit. Suppose we have another part like this. So another part like this. So the what it is computing is that it is negating all of them and then joining them and by the operation AND. So we have W, X bar, Y bar, Z bar, and then I am taking OR operation of these two, and finally I'm getting the function this. Okay, so this logic digital circuit actually representing this function, this digital circuit representing this function. So let's make it more complicated. So I made one more loop here, and then it becomes a function like this. Now see, the size of this circuit is increasing every time you are putting more options there. Okay, so the question is here now. This is what I want to have my function need to work. Okay, but is it the size I need, or can I reduce this circuit by somehow? Okay, can graph theory play a role to reduce this circuit? To demonstrate that, what we are going to use, we are going to use one concept in graph theory that is known as minimal edge cover. Okay, minimal edge cover. So what is edge cover here? It's a collection of edges. Okay, it's a collection of edges. So it's a subset of the edge set of G such that any two edges, any vertex, if you pick up from the graph, it will have one edge incident with it in the set S. Okay, it will have in the an edge incident with it. Say for example, if I consider this graph, then one edge cover for this is selecting this edge and this edge, because this edge is covering these two vertices of the graph, and this edge covering these two vertices of the graph. So these two edges are enough to cover all the vertices of the graph. So we need to find a collection of such edges, and it is called a minimal edge cover. Okay, minimal edge cover. Now we consider a bigger function to minimize it. Okay, so what is that function? This function. So which has even 7 terms. Now 7 terms. Now you can think the circuit that we have constructed, the way we have constructed, how big it will be. Now you'd like to find an equivalent circuit which will do the work of this function. How can we do this? So let us denote each of the literals in this function by some small symbol f1, f2. So this is my f1. Okay, this is my f2, and so on. So and we denote each of these summands by drawing some vertices. Okay, by drawing some vertices, and then we will draw edges among them. So we'll draw edges between f1, f2. Okay, so what is the criteria of drawing edge between f1 and f2? So if you look into f1 and f2, you can see that the difference between this is only in w. The others are same. It is w and it is w bar. The others are x bar, y bar, z bar, x bar, y bar, z bar. So if there is a difference in one of the variable, then only we will draw edge. So f1 and f2 going to be adjacent here. So similarly, f2 and f3, or say f6 and f7, if you see f6 and f7, they differ in w bar only. Here it is w, here it is w bar. So they are different in one variable, the other 3 variables are same, so that's why we are drawing this edge. So this is how we are drawing the graph. Now next, what we are going to do, we are going to find a minimal cover for this graph. So remember, a minimal cover will involve these 2 edges definitely, because to cover this vertex we need to have this edge, and to cover the 7th vertex we need to have this edge. So this edge, 2 edges must be there in the minimal cover. And apart from that, what I'm doing, I'm taking this edge, so this will select these 2 vertices, and I'm taking this edge to select cover this vertex. This has been already covered, but I have to cover this one also. So that is how I'm getting a minimal cover. Now for each minimal cover, the edge represents what? What is the significance of this edge? It means that the corresponding literals, corresponding 2 terms are actually deferred by one variable. So what we will do, we will represent the corresponding edge by dropping this variable from here, dropping this variable here. So it is x bar, y bar, z bar now. So w bar, they we have just dropped them. Similarly for the other edges as well. Okay, for the other edges as well. And it has been seen that when I add these 4 terms, which are associated with these edges, the behavior of this big function, okay, bigger function, is same as the behavior of the same in this smaller function. Okay, so we have reduced it significantly. Now from 7 terms we have 4 terms. Now I can repeat the process. Suppose we have this function now, I can repeat the process. So we are now going to repeat the process to reduce it further. So this is the graph theoretic representation again, okay, for this function, So here these two literals are deferred by only in one variable, that is z bar. So they are adjacent, and the other variables are not satisfying that. That's why they are isolated. Okay. So if I repeat the process, then what I'm going to get for this edge, we have a representation w bar y. So the function reduces further to get it x bar, y bar, z bar, then x, y, z, and w bar, y bar. So this is the reduced function now. So this function and this bigger function will do the same work. Okay, their behavior will be same. Now, if you draw the circuit corresponding to this, you are going to get only this much. Now you can realize how it has been reduced to make it simple. Okay, and a small idea of edge cover has been used to reduce the circuit. Okay, I hope this true application actually ignited in your mind that we must how powerful this subject is from application point of view. Remember, this graphs has application in electrical circuit as well. Okay, for computing the currents in different branches of the electrical circuit, we can apply graph theory, and in fact, the matrix representation plays an important role in this context. Now let's move to another problem. It's at this moment it's looked like a game kind of thing, but there are plenty of scope of doing research in this field also. So we are going to discuss one new type of reachability problem in the graph. Okay. So reachability means when I say that whether I can go from one vertex to another vertex in the graph or not, that is one kind of reachability problem. And when I can go from one vertex to another vertex, now can I go from this vertex to this vertex? Yes, of course, because I have a path from here to here. So whenever there is a path between one vertex to another vertex, you can always reach from one to another. Okay, and if your graph is connected, definitely you can reach from one vertex to another vertex. Okay, but the kind of problems we are going to discuss here is not exactly matches with that. Okay, so what we are doing here is that we are considering one setup, call it configuration. So we put some obstacle in each of these vertices. So this blue circles represent obstacles, and this red one is a spatial object. We call this object as robot. Okay, the term robot I am using because this problem actually get motivated from the modeling of robot motion, discrete robot motion. Okay, when you represent the robot motion on a network, actually it can be represented using a graph. So it is motivated from there. So we have some obstacle in this position, but my aim is to take the robot from this place to this place, this place to this place. So how can I take it? Remember, I need to use only this routes only. I cannot go somewhere from here like this. My routes are this only. Now, can I go from here to here? Can I take my robot to this place to this place? If you look into this, and in fact, what is here in this setup, you can move the obstacle only to this empty vertex, and also robot can be moved only to an empty vertex. So it cannot jump. So it need to move continuously from here. So if I want to take the robot any further, so I have to shift this obstacle to here, so that this become empty, then this to here, then this become empty, then this to here, then this become empty, then so, and then I can bring this empty cell over here, and after that I can move the robot here. But the moment I move the robot here, this becomes empty. This becomes empty. Now I cannot move further because I cannot take the obstacle from this position to this position. It need to be moved along the edges only. Okay, so it means I cannot take the robot from this position to this position in this graph. So I need to give some special powers to the robot so that I can move it. Okay, so that is the motivation of the problem. Okay, so what special power we are going to give the robot is some kind of jump kind of move. Okay, some kind of jumping move, and we call it MRJ move. We call it MRJ move. So what is MRJ move actually? M stands for number of some integer, R means robot, J for jump. So robot is moving, jumping over M obstacles. So you can understand it from here. So, but that jumping is allowed only when you have a path between the vertices from where you want to move one. So for example, I want to move my robot from this vertex to this vertex. Okay, so I want to move my robot from this vertex to this vertex. So I see that there is a path, and then only I can move the robot by jumping. So without path, we are not allowed to jump. So if I jump, it is going to here, and the empty cell will come over here. Okay, this movement we will call 3RJ move, because we are jumping here along a path on which there are 3 obstacles. Okay, but we can also see it as a 5RJ move also. So because we have another path here, if I consider this path for the movement, so then it is a 5RJ move because there are 5 obstacles here. Okay, so this is a 5RJ move if you use the green path into consideration. Okay, now the question is, what are the issues has been solved till now? A 0RJ move, let's see it. A 0RJ move is also known as a simple move. 0RJ means it is moving from a vertex to the adjacent vertex, provided that is empty. So we are not jumping over any. So in our context, we are going to allow the robot to move, allow the robot to have 0RJ move, as well as obstacles to have 0RJ move. Remember, obstacles are not allowed to have any other move. Only robot can have a special move like MRJ move. So this is an example of a 0RJ move of the robot. So this is not jumping over any obstacle. It is going to adjacent vertex. Similarly, this is representing a 0RJ move of the obstacle. The obstacle is moved from this place to this place. So not jumping over any obstacle. It is just moving from its position to adjacent vertex, provided that is empty. Okay, now the real problem. So let us try to understand the problem. So what is it? A graph G is said to be complete MRJ reachable if starting from each position. Okay, wherever you start the robot, you can take the robot in to any other vertex. Remember, any other vertex. It's not like starting from here only to that vertex. You have to be able to take the vertex from any position to any other position in the graph using MRJ move and simple moves. Okay, MRJ moves means you can jump over only M obstacles, and or you can using simple moves means you can only move to this. Both this we are allowing together, and then only we call it a complete MRJ reachable graph. Okay. The classical problem of reachability in graphs is to find a shortest path and move along that path. Okay, it's a very simple one. Solution exists whenever there is a path between 2 specified vertices in the classical reachability problem. But in MRJ reachability problem, it not only depends on the existence of path, but also depends on the structure. Sometimes even path exists, but we won't be able to take the robot further, as we have seen in the beginning itself. We cannot move the robot from the vertex where it was to the adjacent vertex, only beyond that. Okay, so what we know till now is that a biconnected graph is complete MRJ reachable. So what is biconnected graph? It means between every pair of vertices you will have at least two disjoint paths. Disjoint paths, remember. Okay. So you might be having obstacles here, here, here. Okay. You might be having obstacles here, here, like this, and the robot is somewhere here, and you want to take it from here to here. If you have two different paths between these two vertices, you can always do that. So what you have to do, you have to select one path for taking the robot further. So how can you do this? You move the this obstacle here, this obstacle here, this obstacle here. So this become empty. You take the robot here. Now this is empty. So you take this obstacle here, obstacle here, obstacle here, like this. Okay, continue this process. The robot can go and move and move and move, and finally can go there. So that's why biconnected graphs are complete MRJ reachable. For each M, remember M is given to you. Okay. A connected graph with a cycle having M plus 1 or more edges is complete MRJ reachable. So if you have a connected graph in which you have a cycle of length M plus 1. So what we mean by a cycle? So if I consider this graph, okay. If I consider this graph, it is a graph with a cycle. Which is a cycle? This one is a cycle. So as I told you, I will be telling you the terminologies during the time of this. So this is the cycle. Okay. So if you have a cycle of length M plus 1, so what is the length of it? 1 plus 2 plus 3 plus 4. So it has a cycle of length 3 plus 1. So it is this graph is going to be complete 3RJ reachable. This graph going to be complete 3RJ reachable. So that's what this result says. So I'm quickly going through this because I want to discuss the open issues in this problem. A connected graph is complete 1RJ reachable. So 1RJ means you are allowing jump only over one object. So to the robot. So this is also 1RJ reachable if the graph is connected. So see the things when you increase the number, the complexity of the problem going to increase. Now another thing we okay, before I move further, so what we can infer from here is that if I have a cycle in the graph, this graph is going to be complete MRJ reachable. So definitely if I don't have cycle, the problem will be it will be difficult. Okay, it may be difficult. Okay, we don't know at this moment. And also if the graph is connected, this is 1RJ reachable. So it means if the graph is disconnected, if the graph is connected, it is 1RJ reachable. So there is no novelty in studying 1RJ reachability. So that's why we are going to increase it. We are going to consider the problem for MRJ reachability with M greater than or equal to 2. Okay, but remember M is fixed. Once you select it, it is fixed. So what we are going to discuss now, we are going to discuss connected graphs that has no cycle. Connected graphs that has no cycle. Okay, and we call such graphs as trees. A connected graph with no cycle is known as trees. So we are going to concentrate on trees only. We are going to study complete MRJ reachability problem on trees. So we have a nice beginning here. What is observed is that if you have a complete MRJ reachable tree T dash, if you have a complete MRJ reachable tree T dash, and if T is T has this T dash as a subtree, so it means T dash is a part of T, then T also becomes complete MRJ reachable. Okay, so this results motivated us to actually find this result motivated us to actually investigate or looking for minimal complete MRJ reachable tree. Minimal, because any larger tree will contain one of those minimal MRJ reachable trees. Okay, and we started concentrating on finding the smallest trees which are complete MRJ reachable. Okay, now in this process, what we have observed is that this tree T0, we call this tree as T naught. T naught is the smallest complete towards a reachable tree. Okay, so detailed proof is there for proving that this is the smallest complete towards a reachable tree. Uh, okay, and in fact, this is the only minimal complete towards a reachable tree. Okay, minimal complete towards a reachable tree. So any tree other than this is going to have this tree as a subtree. Okay. Remember how many trees we have? Infinitely many. Whichever tree is complete towards a reachable, going to have this tree as a subtree. Okay. So the results that we have here in this connection, a tree is complete towards a reachable if and only if it is either K2 or it contains T naught as a subtree. Okay, K2 means this graph. K2 means this graph with two vertex and both are adjacent. So this is your K2. So this graph is also towards a reachable, and by simple moves it is towards a reachable. Suppose we have a robot. We have a robot here. We have a robot here. This is empty. We can take the robot here, but that's what. No obstacle can be kept because we must have a robot. We must have a empty hole, and the remaining vertices need to be filled by obstacles. Okay, that is what the issue. So any graph that is complete towards a reachable will be either K2 or it will have T naught as a subtree. Now, in search of an algorithm, when I so remember, this process will give you the trees. Will be able to identify. Is giving you a characterization of the trees which are complete towards a reachable. Now, identifying. Suppose I give you an input. See, I give you thousands of graphs. You have to quickly tell me which of this is going to give you one complete towards a reachable tree. Okay. So you need to develop an algorithm. So in the process of searching an algorithm for checking whether a tree is complete towards a reachable or not, we got this result. Okay, so what you have to do actually in the tree, you have to search for two paths. One I'm denoting by P4 and the other by P4 dash. So you search for two paths of length 4. Okay, and if these two paths satisfy this property, so you need to check whether those two paths satisfy this property or not. So if they satisfy this property, you will be able to tell that the graph is towards a complete towards a reachable. So that is how you can develop an algorithm using this theory. Okay, but I hope you have understood the problem. Now let's move to complete 3-edge reachability. So complete 3-edge reachability means we are allowing the robot to jump over 3 objects only. So to understand this, we need to understand the graphs that are complete 3-edge reachable. We need a concept of called tail in the graph. So what is a tail in the graph? So let's understand it. So this is a tail in the graph. Okay, so it should have a vertex of degree more than 2. Okay, so this is a vertex of degree 3, and all the remaining vertices will have degree less than. Okay, so something like this is going to be a tail. So this graph has 4 tails. This is one tail, this is one tail, and this is one tail. Okay. Now, one result that is one thing we have observed that a complete minimal complete 3-edge reachable graph can have tails of length at most 3. Okay. The reachable tree can have a tail of length at most 3. Sorry, it's 3. Now, what is this collection? What is this graph? We are calling it a collection because we are denoting this portion by dotted lines. Okay. So what is that dotted line? It is a path of length that is not multiple of 3. So it means we cannot have a situation like this. Okay. So here the length of this path is 3. So we cannot have a situation like this. Okay. So the length, we have many vertices in this dotted line, but the length of this path is going to be not multiple of 3. Okay. So the collection of all such trees we are denoting by T3. we are denoting by T3. And we have observed that any tree in the collection T3 is complete 3RJ reachable. Okay. The next thing we have observed that a tree T is complete 3RJ reachable if and only if T contains a member of T3 as a subtree. And another thing, the corollary of it is that the members of T3 are nothing but minimal complete 3RJ reachable tree. Okay. So now you see the collection T3 is an infinite collection, and now you can compare with 2RJ reachability and 3RJ reachability. The moment we have allowed one jump, the collection of minimal complete 3RJ reachable tree is going from 1 to infinite. So in 2RJ reachability, we have only one minimal complete 2RJ reachable tree, but when we move to 3RJ reachability, we have an infinite class of 3RJ reachable trees. Okay, minimal complete 3RJ reachable tree. Okay, and that class actually helps you to characterize the whole lot of 3RJ reachable trees. Now, till now, we have been able to solve this problem completely for only 2RJ reachable and 3RJ reachable. Remember, this is open problems, 4RJ reachable, 5RJ reachable, or say general MRJ reachable, reachability in general. What are the things we are going to, what are the issues we are going to have there? Okay. Now, quickly I will tell you the updates about the 4RJ reachability we have got till now. We have got a class of graphs like this. We call it T4.1. T4.1. And what is the length of this? What is the length of this? This length is not divisible by 2. This length is not divisible by 2. So this class is, we have proved that this class is also a minimal complete 4RJ reachable tree. This class is also minimal complete 4RJ reachable tree. Okay. And another class we have got is this class. Okay. So here we have two paths, dotted paths, and the length of these two dotted paths need to satisfy certain property. So what is that? The length should be congruent to A mod 4, congruent to B mod 4, where A and B are from these pairs. Okay, so this is how this class has been defined, and we have been able to show that this class is also minimal complete 4RJ reachable trees. Okay, this class. So we till now we have been able to identify two classes of minimal complete 4RJ reachable tree. Okay, and both of them are infinite classes. Remember. Any tree in the collection T4.1 is complete 4RJ reachable, and in fact the trees listed in T4.LM is also complete 4RJ reachable. So a minimal complete 4RJ reachable tree can have tails of length at most 4. So look into this. Both the minimal trees that we have listed here, the tails are here of length, maximum tail is of length 3. Okay, the other class is having maximum tails is of length 4. So definitely if we have a minimal another class of minimal spanning tree, tails going to be less than 4 only. Okay, that we have already established, but we have not been able to establish minimal complete whether these two classes are the exhaustive class or not. Okay. The class of minimal the class of trees T4.2 is also complete 4RJ reachable. Now the open issues here is that is T4.1 and 4.2 are the exhaustive list of minimal complete 4RJ reachable tree, or we don't know actually at this moment. We have not been able to show that these are the only, or we have not been able to find another class. Okay. Total characterization of complete 4RJ reachable, that means it is open at this moment. We have not been able to say that this graph going to be complete 4RJ reachable, this is not going to be complete 4RJ reachable, or we have not been able to define complete 4RJ reachable trees completely. Okay. Now this is what we have discussed till now, but if you see, we have a more general setup in this context. we have defined, if you interested to know further, we have defined a more complicated kind of reachability here, complete S reachability. So what is S stands for here? When I take a complete MRJ reachability, so S stands for here 0 comma M. So it means I'm allowing the robot move 0 RJ move or MRJ move. Now suppose I take S to be some integers, say 1 comma 2 comma 3 comma 1 comma 2 comma 3. So it means I'm allowing the robot to jump over one obstacle, two obstacle, or three obstacle. All this combination I'm allowing. Now what advantage we are going to have? Okay, what kind of graphs going to be S reachable for a given set of S? Okay, so that problem is completely unexplored. Okay, completely unexplored. We have given some general observation on complete S reachability, but we have not been able to do much on this in this context. Okay, but another issue is I forgot to mention is optimization issue. Optimization issue. So optimization issue means I know that in my graph I can take the robot from any position to another position. The moment I know, can I say that what will be the minimum number of moves of the robot will be required to take the robot from one place to another place? Okay, can we move it with minimum number of steps? Okay, how to find that minimum number of moves, and which path, if I have multiple paths to take the robot from one place to another place, which path going to play the role of a minimum path? We have found example that the smallest path always not going to give you minimum number of moves to take the robot further. So I'll give you some references where you will get this information. Okay, so you see, in classical reachability problem, you always take the smallest path from one place to another place. But the problem we are considering here is that you know that this path is minimum, but that path is not playing the role to give you the optimal number of moves to take the robot from from the present vertex to the destination vertex. So that side is completely unexplored. We have not touched that side of optimizing the number of moves. Okay, now I'd like to ask Devashish. Devashish, can you hear me? I need another 15 minutes if I go to the next topic. I think I should stop. I have already crossed more than 10 minutes.
No, it's okay. It's yeah, you can take another 10 minutes, no problem. It's still
Okay.
1:15.
I will quickly discuss
Yeah,
the social problem that I wanted to discuss.
yeah.
Okay.
You were your title itself was on social problems. Yeah, you may highlight something on.
So now, yes. Now, if you look into till now, you see I have given plenty of scope to give problem to your mind. Okay. So in this context, you can contact me if you have interest in solving any problem in this context. Now let's move to a social problem that I wanted to discuss, means modeling of a social problem, because I wanted to give you a taste in diverse areas of application of graph theory in diverse areas, although it is not possible in 1 hour lecture. So consider this problem. So a MNC means stands for multinational company, want to decide a team for a new project. So they got a new project, say a software company you can talk about. They got a new project and they want to select a new team for that project from the existing members what they have in the organization. Okay, now what they would like to address while selecting the team, each team member should be efficient enough to handle the project, because the project is specific, they have some issues. So each of the members they are going to select whether they are fit for that to resolve those issues in the involved in the project or not. So they would like to see. So that is simple. They would like to resolve before selecting any team member. Okay. But apart from that, see, when you are selecting a team, so the team going to work together. Okay, so company also worried whether the team together going to give a better output or not, and that's why they want to look into the relationship among the team members also, uh, uh, also uh, while selecting the team. Okay, uh, so this is not always going to be considered, but this is desirous. You can see that in the actual context, when the project is very important for the company, they would like to address this issue as well, relationship issue as well. Okay, but how can I identify, or how can I measure whether my team is a healthy team or not? Okay, how can I give analyze that team? Okay, so in this context, we are going to introduce a new kind of graph. In fact, this is not my introduction. It has been introduced in around 70 years back by Professor Harare. So now it is, you can see that you can find relevance in application also. Okay, so what I do here, I want to know whether the each pair of members in the team have a balanced relationship or not. Okay, each pair of members is have a balanced relationship or not. Now the question is, what we mean by balanced relationship? In mathematics, we must have a concise idea, clear idea about when I say the balanced relationship. We must have a clear idea. Okay, so we try to they try to model it in a way. So for that, let's try to understand from this context. So start with two members in the group, say X and Y. So what may be the situation between X and Y? X dislike Y, and Y X likes Y. Y likes X. Okay, so this may be the situation. The other situation may be like this: Y likes X and X dislikes Y. The other situation may be X likes Y, S dislikes Y, Y also dislikes Y, and this is X likes Y and S dislikes Y. Okay, now out of this, they have defined these two as their balanced relationship. Now let's try to understand intuitively why they are balanced. You see, you are working in a group, and X and Y, they are not having a healthy relation. Both and X and Y don't like each other. It means in the context of what teamwork, they are not going to interact. Okay, so when you are handling a project, it has different modules. So company may think that okay, X and Y can be put in different modules where they don't have to interact with each other. So that's why in that context, this relationship is balanced. But when they are interacting with each other, they like each other, then definitely this is going to be balanced. So this is okay, but this is also they considered as a balanced relationship. Now, to represent balanced relationship, we actually remove this directed edges. So we put simply dotted lines and this. So this dotted line means that X does not like Y, Y does not like X. This means X likes Y, Y likes X. And this type of situation we are not going to consider. This type of situation we are not going to consider. But this is not the end. Okay, we have other issues as well. Now, how these two behaving with a third member? Okay, how these two are behaving with a third member? What are the possibilities we can have? Okay, these three possibilities when X and Y are not liking each other. So we have a third person, Z. X likes Z, Y does not like Z. Oh, sorry, X does not like Z, Y likes Z. So something like that. X and Y both like Z, and this is X does not like, Y does not like Z. Okay. So similarly, for the other option also, we have three possibilities. Now, out of this, which of this which is balanced? Can I extend the idea of balancedness further? Okay, can I extend it the idea of balancedness further? So what you can have here is that if I look into this relationship, this is considered as balanced, and this too is not balanced. I will give you a intuitive idea why this is not balanced. This is also not balanced. This is balanced. This is not. This is balanced. This is definitely balanced. Everything is green, green, green. Okay. Now, why it is balanced? Say intuitive idea. Say for example, if Z, if Y is interacting with Z, then X is not going to interact with Z because X is not having any relationship with Z. They don't like each other. They will be put into differently. So that's why if all these three come into together, they are not going to create any issue in the thing. Okay. But when you consider this problem, when you consider this issue, okay, so X and Y, they don't like each other, but X likes Z, X likes Y likes also Z. So if they are interacting, both of them interacting with Z, Z may be in trouble. So they have Z need to satisfy both X and Y, because there is some clash between X and Y. Okay, so in this case, there may be some situation where the situation may be very worst. So that's why this relationship is not balanced, and so on. So you can explain the other cases also. So what we have here is that we have only three cases which are considered to be balanced. This is a balanced case, this is a balanced case, and this is a balanced case. Now, how can I define it mathematically? So what we are going to do in the graph, if I have dotted lines, I will assign some -1 to each of this dotted line and +1 to each of the green lines. Okay, -1 to the dotted lines. Sorry, this is green line, so it is -1, +1, +1, and this is -1. Sorry, I did a mistake here. This I don't need. So this is -1, this is -1, and this is +1. Okay, and here all are +1, all are +1. Okay, now you multiply the numbers associated with the ages in this. So what you are going to get is the product of this age is going to give you +1. Okay, this is also +1 and this is also +1. But if I assign the -1 here, -1, then what is the product I'm going to get here is -1. Okay, and this is also going to be -1 because it is -1 -1, 2 +1s. Okay, 2 +1s. Okay, so we have an interpretation now. Okay, we have an interpretation now. So to do that interpretation, we will formalize the thing and then we'll come. So what we are going to define a new kind of graph that is called sign graph. So what is sign graph? Each of the age, there is a mapping from the age set to the set of 1, -1. So it means each age is assigned with a number from this set. Okay, so this is a graph, and this is one assignment to numbers to the ages. So now we are not using green lines and dotted lines and solid lines. You can see that this is -1 -1 everywhere, and then +1 -1 like that. Okay, so -1 represents unlike, and +1 represents like. And we have defined they have defined one concept called balanceness. So what is balanceness? So for that we need sign of this also. By sigma e we denote the sign of the age e, and if I take any subgraph of the graph sign graph sigma, then product of the sign of the ages of the subgraph is called the sign of the subgraph. Okay, so a graph is balanced if and only if each cycle in G has sign 1. Each cycle in G has sign 1. Now when we go to cycles, it looks like something. It looks like something like this. it is a cycle. It is a cycle. Okay. So if a graph has a cycle like this, so it means it is not balanced, because this cycle is not balanced. Okay, this cycle is not balanced. So Harari actually gave characterization of this balance graphs, and they have found that a graph is balanced if and only if all paths joining the same pair of vertices have the same sign. Or another significant characterization is a sign graph is balanced if and only if its vertices can be partitioned in two subsets such that each positive edge joins two vertices from the same subset, and each negative edge joins vertices from different subsets. So you can see that this idea was given in around in 1960s, 1950-60s. So it has been used in many contexts, but I have not seen it in using this idea to select a team for a project. And I hope that this can have an application in selecting a team for a project to have a better output. So that's why I have decided to give the introduction of this problem. I think I have shoot the time at least by 20 minutes, but I will stop here.
Yeah. Yeah.
Okay. And
Yeah, if you are done,
definitely I would like to have
with,
any questions if any of the participants have. That's
yeah, there are some questions. So first of all, I'd like to thank Biswajit sir for this wonderful presentation, and we are very happy that he took part in our. This is the first initiative by Department of Mathematics, Gurucharan College, for an international webinar.
in fact, it was
So I am
my
very happy
pleasure
that
as well.
yeah, I'm very happy that Biswajit sir has taken part in this. Sir, you can remove your screen sharing option so that you can see the questions as well. Stop sharing. You can click on stop sharing. Yeah, and the questions. Okay, let us go to first. Okay, just let me test whether you are being able to see the questions or not. Uh, the questions will flash on the screen.
I'm on two screens right now. Yes, I can see the
Okay.
questions. No issue.
Oh, you can see the question. Okay, okay, okay. So first of all, let us go to Anirban sir, who is live there with us. Yeah,
Anirban, good morning.
yeah.
Yeah.
So
Hello, Vishweta. Good afternoon.
Hello. Good
And
afternoon.
first and foremost, thank you very much for such an very nice presentation and so clear presentation, along with all the thing tracing around the vertices, edges. I mean, it was very, very clear. Of course, I'm not a very good student of graph theory, but still it was a, I mean, I could definitely gather many informations from that. I might be wrong. I have just two questions in my mind. If you feel the questions are irrelevant, please tell me that. No, these are
No, it's
baseless
okay.
questions. Okay.
Irrelevant questions are sometimes more relevant.
Yeah, that's true. Yeah, with that understanding only. See, in that graph, so when you are showing, this robot is moving from here to here, unless there is an empty vertex, you can't move like that.
Yes.
Something like that you are showing, and later on you were explaining something about that the partitioning,
Uh,
the vertices part. I just wonder, I mean, the same thing can we do in terms of relations of functions and matrix separations? Is it equally interpretable there also?
you see, this problem, I have been stuck to this problem. I have solved this characterization up to 3RJ reachability in almost 3-4 years back, and then for last 3-4 years I am trying to actually characterize 4RJ reachability. So we have been able to identify two classes of graphs, and in fact we have been able to prove that these two classes are 4RJ reachable. So I am trying to apply many concepts, but I have not thought about applying this relation and all these things into here. But definitely, if you have an idea, better idea, or you can incite some application of it, definitely it will be helpful for us also, because my students, one of my student is working on this problem, so it will be in help for him also.
I mean,
If I have
for me also, the graph theory leads me. I think it might be true for you also. Kuntola Patra, madam, our ma'am in the God University,
yes, yes.
and ma'am also used to tell Harare today. You have also mentioned about many observations by Harare, and I have with my limitations of graph theory things, but I was able
Remember,
to.
one of the classical book on graph theory was written in first actually book. Good book was written in 1969 by Harare, and till
Okay.
whoever actually teaching graph theory, they tell students to refer that book first and then the
Yeah,
other
yeah,
books. So
yeah,
that's
yeah.
how
In
Harare
fact,
is so much of important till date, after
yeah,
70 years
true. I
as
mean,
well.
yeah, it's the ultimate book. In fact, I happen to teach some of my MTech computer science students for their data analysis and data computer networks.
I think
So,
some internet issue has come.
am I audible?
So it's
Am I
It's
audible?
started raining
yeah,
out
it's
here, so
audible.
let me else if it works better.
I think yeah, it's audible.
Okay.
It's audible, right?
Yeah.
Oh yeah, yeah.
Okay.
Okay. So let us
Fine.
take up some more questions now. Thank you, Onivan
Sure,
sir.
sure. Yeah, thank you very much.
Welcoming you backstage. Yeah. So there is one question here from. You can see the question on the screen also. Is it used in robotics as well as cryptography?
Uh, uh, the emergent reachability problem that I have discussed here is actually inspired by discrete robot motion problem only. So robot actually moves point to point. They don't move in curve. Now advanced robots are coming up. They also moved in a curve, but still many of the robots move point to point. Okay, so when you want to move a robot from one position in a setup, so need to move from point to point. So suppose you have a setup where you have obstacles, so the robot need to either remove the put away the obstacle, or it need to bypass. So that's how, if you model it in a graph, it looks like similar to what we have discussed.
Yeah.
But in that modeling, only zero RJ moves is allowed. Means you can move the robot from present position to the adjacent empty vertex. Okay, uh, but that's how it has application in robotics. But the kind of problem we are investigating is that if your robot has a spatial power of jumping over obstacles, so now it may not be having, but in future if you develop robots jumping over obstacles, and if you have a network in which your robot need to be moved, so you have to prior to put the robot for some work in that network, you need to know whether my robot can reach from present vertex to the destination vertex or not. So in that context, this may be useful, in fact.
Okay. Thank you, sir. There is another question here. Let's see. Shodobnath, is there any connection between linear algebra and graph theory? Lots of connections.
Yes, I wanted to discuss, but yesterday night I dropped the linear algebra portion deliberately, because it was going too long. Because
Yeah,
only introducing a concept and not giving you some insight on that, it's not good. In fact,
it's a big topic
matrices
actually.
are the
Linear
base
algebra.
representation of graphs.
Yeah.
Matrices are the base representation of the graphs, and I would like to suggest you one book written by R.B. Bapat sir, from
Yeah, Arbi
ISI, Professor R.B. Bapat sir from ISI Delhi.
Delhi.
Graphs and matrices. Cost is around 250. It's a nice book. In fact,
Yeah.
written very concisely, giving you the concept how means graphs and linear algebra marry each other, and
Yeah.
how the interesting fact is that how you can use graphs to define the determinant of a matrix. Okay, how you can count the number of spanning trees of a graph using some say cofactors of matrices. So that's how graph and matrices, they are actually nowadays spectral graph theory, in that portion, it is nothing but two sides of the same coin. They are not
Yeah.
separated by anything. They are together.
Yeah. In fact, I am also working on this combined idea of linear algebra and graph theory.
Yeah, I know.
Okay. So we have another question here. Okay. Yeah. Let us see what is this. Oh, it's from the same person. I have studied little about graph theory in my last sem, but after knowing such aspects of and great application of graph theory, I am very much interested. Okay. So that's a compliment
Yeah,
you
that
deserve.
was the motive of this webinar as well as this lecture as
Yeah.
well, to
Yeah. To motivate the students to
motivate you to take this subject, because this has you have plenty of scope doing research in graph theory and its
yes.
application. In fact, you can work on engineering as well as scientific field by staying into mathematics field. That's
Yeah.
what, and in future you have to be like that only. You cannot do mathematics only.
Okay. So these are the questions. I don't think there are more. Okay. So on behalf of the Department of Mathematics, I'd like to extend my heartfelt thanks to Biswajit sir for this wonderful session. And for the participants, we have already provided the feedback link. You will also get the feedback link in the comment section of the video in YouTube, which will remain permanently. So you can please try to fill it up today itself. And we'll be back for the next session today at 4 at 3:45. We will be live. We will not be live means we'll be ready to go live. So we'll go live at 4 for the next session by Dr. Manjil Shaikh. So till then, thank you. I am closing the broadcast now. Thank you.
Okay, thank you, Devashish. It's my pleasure to be here. Thank you.
Thank you. Thank you.